So, I think we are about to start. So, those of you who haven't noticed, we slightly changed the program. So the first talk will be about squeezing attack traces for about half an hour, I think. And then it's, thanks for the back trace then. And then it's followed by the one that was originally scheduled for now, hacking into botnet, exactly into the Storm botnet. For me, this is kind of an unknown territory, so I don't know if I've any active experience with a Storm bot or any bot, but yesterday I heard about a Chinese bot on a stick, and now I don't know really if I had some passive experience with a Storm bot or anything like that. I hope you guys will tell me something about taking bots apart, looking at what makes them tick, and I'm really interested in knowing more about that. Hopefully, as you all are, and that's for you. For a warm welcome, please give a hand.
Okay. Hello, everybody. Does this work? Yeah. Okay. Yeah. Hi, this is Markus, and my name is Tillmann. We will be giving you a quick introduction to what you can do with honeypot data. So our first question is, who of you is not aware of what a honeypot is? Yeah, okay. For you, sir, you can think of a honeypot as a sensor, some kind of sensor, which basically has its value in being attacked. So it's a box or a resource on the internet, probably, and it's waiting for being attacked. And if it gets hit, then the goal is, or its task is, to record as many information about an ongoing attack as possible. And then you can take this information and try to, mine it or do funny things with it. And this is what our talk is about. So after having fixed the XORG stuff, we can start with our first slide. First of all, we need an environment. So like a monitoring setup, which allows us to record the data. And what we want to do is we want to squeeze attack traces. So we want to get as much information out of them as possible. So first question, which is an appropriate operating system? We thought, okay, we are Unix gurus. We like to use Linux, but there's a slight problem, because if you use Linux, there's hardly any attacks, or only a few attacks, like those plain SSH, password brute forces and stuff. But if you use Linux, you are not really vulnerable to the big majority of attacks which is going on the internet. So if you choose Linux, your life is kind of boring. Nobody's hacking your box. And we thought about how can we fix that, and our approach is attacks are happening all the time. So if you link a box to the internet and sniff the network or something, then you see ongoing attacks all the time. But these attacks target Windows operating systems. So we thought, okay, let's fix Linux in a way that Windows exploits can harm it. And yeah, as you can read here, the solution is to turn Linux in a system vulnerable to those. And if we succeed, our box will finally be being able to get hacked. Yeah. Okay, so let's assume we have a Linux operating system which is vulnerable to Windows exploits. The next question is, how can we attract the bad guys? So basically you. Yeah, we can give a talk here, publish IP addresses or something, and hope that you will probe these afterwards. But this is, not even necessary. Because as I said before, attacks are ongoing all the time. We can just link our box to the internet and wait. And from our viewpoint, an attack begins with a connection, of course, in the network. It's not a connection in the sense of TCP, where you have a full duplex stream-oriented connection. We also understand a UDP session as a connection. So that's our understanding of a connection. And a connection basically transports malicious data. Okay, the first goal for us is to trap these connections, so to make them actually make them being established, and then to record the data which is transmitted over this connection, and afterwards we can squeeze that. Luckily, there's a little tool called Honeytrap, which was implemented as a low interactive honeypot, which also already provides us with this functionality. It can bind to UDP and TCP ports dynamically, so you can imagine of like a sensor which sits on the internet and behaves passively, so no ports are bound, no services are started, and once you connect to it, it dynamically opens up the port and handles the connection or serves you with some data. And this is a nice thing, but there's a slight problem, because if you connect to a port, you certainly want to speak a specific protocol. And if you use this approach of dynamic listeners, as we call it, you have no protocol behind it. And even if you would put, let's say, for instance, HTTP or something behind it, it would be kind of limited, because if you connect to my Honeytrap sensor and want to speak SMTP or something, it must react in the way you intend. So our question is, how can we deal with that without implementing hundreds or thousands of protocols? We need a generic way to do that. So as you can read here, handle connections in a generic fashion. The answer to this is the mirror mode. The mirror mode, let me check, do I have a picture here? Yeah. Okay. Yeah, a picture is nice. Okay, we have, on the left, we have our technically interested person, TIP. The technically interested person connects to our honeypot. Here you see a SYN segment. And in our setup, the SYN segments gets freezed by Honeytrap. So Honeytrap tells the kernel, freeze this SYN segment, I will come back to you later. After that, you have time to fire up a server on that port. So you call a socket, listen, bind, listen, and so on. And then you can unfreeze the SYN segment. So you have started a dynamic server which can then handle the connection. Okay. The fourth step is to mirror the connection, to proxy the connection back to the initiator. So if he sends some data to me, I send it back to him on the same port. So I connect to him on the same port, and I mirror data to him that he sends me to him, and vice versa. So he's basically hacking his own box, if this works. And it works in most of the cases, because this is one of the impressive outcomes. We didn't think that it would work that well, but it actually does, because the situation on the internet, at least it is our explanation that the situation on the internet is like this. Someone is probing your box, mostly infected by some bot or automatic exploitation toolkit, and he was probably owned before himself. So he's vulnerable to the same exploit, and if we mirror the connection back to him, we get a valid exploit trace or intrusion trace. And let me check, do we have our first demo here? Yes. Okay. Tip fail. I have something which I recorded about a year ago, so thank you, which is the old SSL2 open exploit. For those of you who remember that one, it was published in 2002 as a Heap Overflow exploit, published by Solar, what was his name? Solar Eclipse, I think. This is the buffer filling stuff or something, I don't know. And the interesting part is at the bottom. Okay, you see here, at the very top, he starts with the term export, blah, 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 exec bash. And the next line is interesting as well. Uname A, ID, W, and so on. So who's actually currently logged in? Am I the only intruder here and stuff? And most importantly, he sets colors. He sets, to have colorful output. Okay. And I guess this is part of the automatic exploitation thing. And after that, the fun begins. He CDs to var cache mod SSL, ls, cd choice, law. He doesn't even recognize that it's his own directory tree he's browsing here. Then he wgets netracing.com from netracing.com call tarball, extracts it, and so on, executes loginx, sus to root, unset his file, plain old hacker stuff, you know, ID and so on, and then he then he extracts its sbin tarball, bin tarball, and so on, and installs this on his own box. So after that he's rootkitted, and yeah. I don't know if this guy found out actually, because I mean, you know, a rootkit hides the traces, and yeah. Another interesting thing is that we get the rootkits for free here. We can also wget the tarballs and get rootkits for free. Actually, the whole scheme here is a nice thing for collecting exploits, because you don't have to write your own exploits. You basically sit on the internet and wait for the exploits to come into your honeypot, and then you can take them and reuse them. Okay, back to the slides. Yeah, the backgrounds and benefits. Why does it work so nicely? As I said before, the tips are most likely to be vulnerable to the same exploit themselves. And as we do not require any knowledge about the protocol or the service being exploited, it's also suited for novel stuff, so for zero-day exploits and stuff. Yeah, and the advantages from the tip viewpoint are the thing is completely passive. There's no scanning required, so this is not the tip as before, it's us as a tip. From our viewpoint, the exploit collectors, we don't need to scan the internet, we just can sit there and wait for the exploits to arrive. We get boxes for free, you know, like the rootkitted box from the guy before. We get exploits for free, we get malware for free, so yeah. Okay, back to our topic. What can you now do with the exploit traces? You want to squeeze it, we want to get information out of it. One thing we recently developed is you can actually generate an intrusion detection signature from the exploit traces. And you can do that fully automated, in a fully automated manner. So the first step is our sensors, our honey trap sensors collect attack traces. The next step, I'll only provide a brief sketch here. If you are interested in this particular thing, you should talk to me afterwards. The next step would be to automatically cluster or classify the inputs. So you group together the RPC-DCOM exploits, the MySQL password brute forces and stuff. Yeah, because you want, of course, you want one signature for the RPC-DCOM, one for the ELSAS exploit, and so on. So step 2 is a classification step. Step 3 is to identify invariant parts in a cluster. So this is the invariant parts are these parts, the parts who are suited for a signature, because they describe a cluster, and you can take these as a pattern. You can construct a signature from these and publish them in a usable format, which is actually a snort rule. I was planning to give a short demo here. Markus, if you could take the microphone for a second. We recorded some exploit traces against port 8800 TCP this summer, and nobody was able to tell what was behind that. So the vulnerability was unknown, the exploit itself was unknown, so nobody knew what was going on there. And we didn't only see the scanning, but we also recorded some exploit traces. These are 20 traces, about 20 traces, and we will now try to generate a snort signature from these.
We tried before, so it works.
Okay, this is how these exploit traces look like. This is actually what Honeytrap dumped into a file from a session. It's obviously an HTTP GET request, which has 2 parameters or 2 arguments, a user agent parameter and an authorization basic thing. The authorization basic is rather boring because it's a constantly repeating pattern, if you can see that. And the user agent is interesting. It starts with some ASCII crap and then some binary bytes, which looks, if you are familiar with that, like ASCII encoded shellcode, or an exploit at least. And yeah, as you can see here, all of the traces have different MD5 checksums, so they are different actually. But we will now try to extract a signature from these. Okay, I'll now start the Nebula Demon. The Nebula Demon is the signature generation engine. You can provide it with a secret so that you can, submit inputs to it in a secure way. How do I open the second tab here? Okay, and the Nebula package, which is open source, you can download it and play with it yourself, also comes with a command line client to submit files to it. Okay, I just did that. I submitted the 20 files. I guess I missed a parameter here. Yeah, I have to tell it that it should start generating signatures as soon as it has at least 20 traces from one particular attack. And I'll do so now. I'll do it again. Yeah, and as you can see here, a little bit, it's not so easy because the line sizes. Yeah, okay. Yeah, it basically generated this NOT signature, which identified as invariant parts the GET request, the start of the GET request, user agent string. I don't know what that is, probably some, to have the right offset or stuff. And here's the binary data, which is a GET PC sequence. As you might know, in a shellcode, you need to, in most cases, you need to determine where the program counter points to. And this is a typical sequence. I guess we will have that in your part as well, in more detail. This is a getPC sequence starting with a jump, another jump in the core, and this is static over all traces. The short content parts here are probably crap, like noise, and if you would provide more than 20 traces, like 100 or 200 traces, they would probably get eliminated. And the authorization basic part is constant over all traces, so it's completely copied into the signature. And you can now use this signature within Snort to detect exploitation attempts of that kind. Yeah, we don't have more time to talk about signature generation here in more detail. I'll now hand over to Markus, who will give you an introduction to automatic shellcode analysis.
Hello, I'm Markus, and I'll try to explain the basics of detecting and profiling shellcodes from network streams. So taking the technology Till just presented, we can gather a lot of data, and we need a way to automatically look for shellcode within this data. And there are several different approaches to detect shellcode. But the most known approach is manual analysis. Manual analysis is pretty time consuming and it requires Windows. And as Till already mentioned, we were looking for something to make Linux exploitable to Windows exploits. How to detect shellcodes? There were static approaches, detection of NOPE slides. It's pretty historic, nobody does it anymore. There are too many possibilities to create valid NOPE slides. Detection using pattern matching for the decrypting part of a shellcode works, but the more patterns you have, the slower it gets, and it's pretty easy to create new decoders which do not match any signatures. And there were some dynamic approaches, and these are titles of publications. It's about detecting shellcodes, self-decrypting shellcodes, using a technique which is called getPC. Self-decrypting shellcode got a stub in front of the actual payload, and this stub is meant to decrypt the shellcode. You have to encrypt shellcode if you want to avoid certain patterns, for example, a string terminating 0 or something else. And you put a stub in front of the shellcode, which decodes the shellcode before you have encoded it with a XOR pattern or something like that. To be able to decode the shellcode within memory, you have to know where the shellcode actually is. And as you can't access the program counter or EIP register directly, you have to retrieve this, the address. And there are two possibilities to retrieve EIP. One is call. EIP gets pushed on the stack, and you can pop it, or using FPU commands. Looking for these instructions is pretty cheap. There are just 1 or 2 bytes you have to check, and can be done in real time, more or less. The problem about this was all just paperwork. They just said it works, and we did some research on it, but nobody published code. So we had to do our own. We started a project called libemu. We took the knowledge gathered from the papers to implement a small x86 CPU to detect shellcode in network streams. We wanted to use the getPC heuristics just mentioned, binary backwards traversal, I'll explain it later, and instruction dependency tracking to detect shellcode. Furthermore, we wanted to allow shellcode emulation. Once we detect it, we might want to execute it and publish the code before publishing anything else. So, as mentioned previously, how to detect the start of a shellcode. We are looking for getPC sequences. And once we found a getPC sequence, we can't be sure it's actually shellcode. It can be anything. So there has to be a way to check if it's really shellcode. Others have proven that the occurrence of a loop after a getPC sequence is a reliable indicator for shellcode, or 7 payload reads, or 32 steps after the getPC sequence. Going further, we said if you got an AP call within a network stream, it's shellcode too. What now? We need to be able to execute the shellcode within an emulated environment. This emulated environment is a process environment of Windows. And we have to be able to hook AP calls. So we see which AP is meant to call. For example, if the shellcode wants to download something, we want to know where it wants to download from. If the shellcode wants to connect to somebody, we want to know where it wants to connect to. And we've had a lot of problems. One problem was Windows. And the Windows problems were about the process environment block, the DLL loading. A shellcode has to resolve addresses from functions, and it takes a real procedure to get the address of a process function in Windows. On Linux, it's just calling an interrupt. So we have to map the process environment block of a real Windows process to our process environment within our emulation, and the exports of a DLL, of several DLLs as well. For example, we have to provide the exports of kernel 32 DLL and W232 DLL and some others. And another problem is shellcode can have initializing seeding functions before getPC. So we found getPC, and we start executing the shell. You're starting to sleep. There is a chair free in the front. I'll show it in a picture. This is the get PC sequence, you can't see the call, but it's the box above the arrow which is green. I didn't expect it being... So, the problem is we start executing the shellcode in the middle, and there are instructions in front of the shellcode, in front of the getPC sequence, which are required to make the shellcode work. For example, here is a loop as an instruction, and what? And loop requires the ECX register to be initialized, but it was not initialized before. To be able to execute the shellcode properly, we have to look for the instruction which initializes ECX properly. Can you see the red one now? The red path is the one which initializes ECX. And once we start execution on the proper beginning, we can access the encrypted shellcode. Now I'll try to give a short, brief demo of how to use it. We got a small command line interface to the library, which allows executing Windows shellcode on a Linux system, and you can create graphs of it. The command line utility is called sctest, and we will run several different things. The second one means interactive. Interactive allows proxying operating system calls to the host operating system. So if the shellcode wants to download something, it downloads something. This allows tracking shellcodes which consist of multiple stages. The first stage just exploits and opens a port or something like that, and then accepts a connection and executes the data which comes from the accepted connection. To be able to profile such shellcodes, we have to be able to run them interactive. And the other thing is you can create graphs of the shellcode. How does it work? So you can see which AP calls are met and which loops are in there.
Yeah, I assume that there are no open questions to that part, so we can safely skip the demo. No, okay.
Kannst du auch was zu sagen?
Yeah, the thing is that it's actually a nice tool and it's great. Yeah. But it's not so easy to talk about. Okay, Markus is now running sctest, which tests the file piped into it and checks it for shellcodes. Minus G means get PC. Yeah.
Minus G means detect the start of the shellcode using the getPC thing I tried to explain. Minus S means run about 10,000 steps, so it doesn't run forever. It stops after 10,000 steps. Won't be enough. It's Windows shellcode. And the large S means read the data from stat_in. So after 177,000 steps, we can see what the shellcode did. It loaded the library, the WS232 library, which is required to do network communications on Windows, WS startup, WSA socket, bind, listen, accepts the connection, creates a process which with the with the command line command, and uses the handles for this connection from the socket just accepted, which are here. This is the socket which was accepted. So all input from the socket is directed to the new created process, which is the command line, and all I/O which is coming from the connection is given to the command line. Ja, jetzt mache ich das mit rein.
Yeah, the output is actually pretty easy to interpret. It's an execution trace of the shellcode, and you can, it pretty prints the API calls and system calls, so it's a nice thing. But if you are interested in this, you should play with it yourself and try it out.
It's a good possibility to remind you of our workshop.
Yeah, there's a workshop tonight starting at 8 p.m. And we will give you the opportunity to try this out yourself. So it's a hands-on thing, and you will set up your own honeypot there and record some traces and also search for shellcode there.
So now we start the start a C test again, and we say interactive. Do what's required to do to be like Windows, and we can see the process got a port open. And we got a Windows shell.
And now you can run Notepad and do Windows stuff. Yeah, it's wine. Wine is nice because wine is a more or less one-to-one implementation of Windows. I guess they call it bug by bug implementation or something. And you have a it only needs a very small amount of memory. You have a wine directory, .wine directory in your home directory, which can be as small as 2 megabytes or something. And this is basically your emulated Windows environment. And it's easy to flush it after an exploit and set up a new clean wine environment. Okay, the last thing we are going to show you is how libmu can draw graphs of shellcode. You have seen one example in the slides already. Yeah.
You can zoom in and it makes great posters. Yeah, I won't try to explain it.
It's self-explaining.
Yeah, pretty self-explaining. That's it.
We're already, thank you. We're already a little over time, so are there any questions? Okay, there are, okay.
Okay, I have one question. These technologies or similar technologies are used in antivirus software for heuristics. I know about one antivirus that uses something very similar. The question is if it would be possible to use this technology to detect worms and viruses in ClamAV or something like that. That's the first question. And the second one is, can the shellcode do actually something nasty to the machine? Is it closed in a sandbox, or can it do some harm to the computer which you are using? Thank
Yeah,
you.
okay. Okay, your first I guess I'm going to answer your first question and then hand over to Markus. So the first question was, is this technology used in any antivirus products, right? Yeah, you can actually, you can of course use it in antivirus products. It's not used as far as we know yet. So of course we use it to collect malware, analyze it, play with it and stuff, but it's not used in commercial products as far as I know. And yeah, for the second question, I hand over to Markus.
I lost the second question.
The shellcode irgendwie dann
Whether the shellcode can harm the host operating system. One thing is the whole emulation can simply segfault, happens. And the other point is, as long as you don't allow the shellcode to proxy operating system calls to the host operating system or run it interactive, there is nothing you should be worried of.
Yeah, but I must say, and we have talked about that before, if you run the shellcode in interactive mode, you can actually use or write specific shellcode which harms a third party. So when it gets executed on your emulation, it can maybe scan or exploit a third system. Yeah. Any other questions? Otherwise, we will start with the Stormfucker talk.
Have you tried if the honey trap is also working with encrypted connections, 80 GPS, for example?
With what kind of connections?
SSL or TLS.
Yeah, okay. Okay, the question is, does Honeytrap work with encrypted connections? It does, yes. I tried it at least for SSH, so you can log into your own box via Honeytrap proxy, which mirrors the connection back to you. And from that experience, I assume that it also works for TLS and SSL. Of course, you capture the encrypted data, which is not of much value, but yeah.
So it's not opening up the connection with two TLS tunnels, for example?
It doesn't split up an encrypted connection, no. No. Any other questions? No. Okay, for the Storm talk, we will give out beers for everybody who places a smart question. We cannot do this for the former talk because otherwise we would run out of beers. But we have 6 beers here, so if you have a smart question, you can place it in the Storm talk.